All right, so right now we're going to actually move into solving these electrical force problems, but there's a couple of steps we have to go through before we get there. First of all, you got to convert to the correct units. That mainly involves charge, the Q1 and the Q2. Charge units have to be in coulombs, and most of the time we'll be given information in like millicoulombs or microcoulombs, and I'll talk about how to deal with that in just a minute, how to convert from that. Once you get that, you got to sketch the system. Really what that means is figure out whether this force is going to be attractive or repulsive. That's all we really need to do. Then we're going to use Coulomb's law, that equation that we went over, to find just the magnitude of the force, really the direction. That's where we get the direction from sketching the system. It's either going to be attractive or repulsive. That's the diagram, sketching the system. So these steps are really kind of silly. We shouldn't even do that. We're going to check the units and then report the answer. Let's move on. So this is the diagram I'm talking about. I want you to look at this diagram of your notes, and this is sketching the system. All I want you to do is to draw the force of object B on object A, and draw the force of object B on object, or A on B rather. In other words, all I want you to do is draw a diagram here of either attraction or repulsion depending on what's going on. Take about 30 seconds, pause the video, and do that. All right, hopefully you've done that and you can figure out that A is positive and B is positive. Since they have like charges, they're going to repel each other. That's really all we need to know. This is why it doesn't really make sense to say that the force is negative or positive, because we have one going to the left and one going to the right. Negative really doesn't make sense. This is just going to be a repulsive force. But if we have one positive and one negative, they're going to attract each other. Therefore, that is going to be an attractive force. That's the direction for this one. All right, and so then let's look at these practice problems. All right, so you should have this filled out. There should be two arrows doing like this. That's attraction. This is repulsion. Let's look at this problem here. Two charges are separated by 3 centimeters. First of all, when you read this, you should be thinking centimeters has to go to meters. So this is 0.03, 2 decimal places to the left, and they're giving you the distance there. That's how far apart the charges are. Object A has a charge of 6, what is this? This is microcoulombs. This is the Greek letter mu, which stands for our prefix micro. This is not the unit we want this in. It's got to go into coulombs. I'll talk about how to do that in just a minute. But 6 microcoulombs. Object B has a charge of 3 microcoulombs. What is the force? What is the electrostatic force on object A? And really, it's the same as the electrostatic force on object B. The force is the same in both directions. First of all, I want you to draw a line down the middle because we're going to talk about conversions on this side. We first of all have to review how to convert between units, because I know it's been a while since we've done that. So remember, we had our nice cute little number line here in the middle where the decimal was. That's where our base unit went. Anything without a prefix. And in this case, with charges, the base unit is the coulomb. If we go 2 places to the left, that gives us the prefix centi. Centi means times 10 to the negative 2. One more place to the right, sorry, not the left. To the right, one more place is milli. That's times 10 to the negative 3. And then if we take 3 more to the right, that is micro. The Greek letter mu represents the prefix micro, and micro is times 10 to the negative 6th. Literally, these prefixes mean exactly what their exponents are. So when I see a charge of 6 microcoulombs, when I see micro, I can literally substitute in times 10 to the negative 6. So 6 microcoulombs, to convert it to coulombs, micro means times 10 to the negative 6. I'm just going to plug that right in there. 6 times 10 to the negative 6th coulombs. Congratulations, you have just converted from microcoulombs to coulombs. All right, so let's set this up. I know that this is the equation we're using. It's the electrostatic force equation that we talked about on the first video. They want to find the force, and we're given all this other stuff. They don't give us K. I was thinking K and wrote it down. They don't give us K because K is in the chart. That's a given. You should know what it is. K is 9 times 10 to the 9th. Q1, I'm going to say this is charge number 1, but we don't put 6 in. Remember, we convert it to coulombs. So this is 6 times 10 to the negative 6th. And this object B will be charge number 2, but it's not 3. It's got to be converted to coulombs. So this is 3 times 10 to the negative 6th coulombs. divided by the distance, which is 0.03, and that's squared. So we're going to plug all that in our calculator. Take a minute, pause the video if you need to, and do that. If you did that, you should have found that the electrostatic force was 180 newtons. But this is only the magnitude of the force. If we look up here, we see these two charges. They didn't tell us that they're negative, so we can assume that they're both positive charges, which means that this force is going to be a repulsive force. That's the direction that we report for the electrostatic force. It's repulsive. Let's go to the back of the notes. We have a few other practice problems in here. I'm going to work these two with you, and I'll leave this one. I'll just tell you right now the answer to the third practice problem is 45,000 newtons, and it's attractive. It's an attractive force. All right, but let's do these first two together. We have a negative charge of -2 times 10 to the -4, and a positive charge of 8 times 10 to the -4 coulombs. The first thing I'm thinking right now is this one's negative, this one's positive, therefore it's going to be an attractive force because they are unlike charges. Once I know that it's an attractive force, that's all I really care about in terms of the signs. This negative, I can just get rid of it. Now, don't get rid of these negatives in the exponents. You have to keep those. That exponent, you cannot get rid of the negative. If you do, it'll change the number entirely. But you can get rid of the negative before the charge itself. This is our distance. They want to know the force, right? So the electrostatic force, this is our equation, K times Q1 times Q2 divided by D squared, right? Let's plug in 9 times 10 to the 9th. Q1 is 2 times 10 to the -4. That came from right there. I took the negative out because, again, I don't need it. The only reason I need that is to know that it's going to be an attractive force. Once I figure that out, I can get rid of it. 8 times 10 to the -4 goes in here because that's our other charge. And then our distance, 0.3 meters, goes on the bottom, and it's got to be squared. Realize that we didn't have to do any conversions here. Both of these are in coulombs, distances in meters, and we're good to go. If we multiply these on the top and divide by the distance squared on the bottom, you should come out with a force of 16,000 newtons. And again, it is an attractive force because one is positive and one is negative. The work on this stuff, as far as putting it into your calculator, is just something that you're going to kind of have to figure out, but make sure that you can get 16,000 newtons with this. All right, we'll do the second one, and then we'll be done with this video. Again, the third one I'll leave to you. You should get 45,000 newtons. It's an attractive force for that one. The second one, 2 protons. You should be thinking right now, a proton has a positive charge, right? So I have a positive and a positive, therefore this is going to be a repulsive force. They're separated by this distance. What is the magnitude of the electrostatic force? So they want to know Fe again, right? So this is going to be our equation, just like it has before. But you might notice that there's something wrong with this one because all we know is the distance. They want the force. We know K, that's a constant, but we're missing the charges. And so you might be thinking, well, what's going on? Well, remember, on the very front side of the notes should look like this. The charge of 1 electron and 1 proton is equal to 1.6 times 10 to the -19th coulombs. That's in your equation chart. I believe it's number 74 in your chart. It's back there somewhere. But that's the charge of a proton. So anytime you have a problem dealing with a proton or an electron, they're not going to give you the charge. They expect that you know that the charge, Q1 is equal to Q2, since they're both protons, that the charge is 1.6 times 10 to the -19th coulombs. So that is our Q1 and Q2. So we can come back in here and plug those in. K is 9 times 10 to the 9th, just like it always is. What I'm going to do, since Q1 and Q2 are the same thing, really that becomes Q squared. So I can put this in here as 1.6 times 10 to the -19th and then just square it. It gives you the same thing. Divided by the distance squared. Distance is 1 times 10 to the -11th, and that's got to be squared. If you multiply all those together, you should come out with 2.3 times 10 to the negative 6th newtons. And again, it is a repulsive force because they're two positive protons.